In this tutorial, I want to talk about titration and pH graph or pH curve, how to draw that. There are few cases, few possibilities. After salt hydrolysis, it's good to talk about. Titration is a process when you add an acid to a base or vice versa, and the reaction goes through neutralization. You produce a salt. Now, if you remember your salt hydrolysis, if you have strong acid and a strong base, your salt will have pH equal to 7, which is neutral. Now let's see what happens. And in this case, we are adding strong base to the acid, which is already sitting in the flask. So in this flask, you have 50 cm cube of 0.1 mole per decimeter cube nitric acid, strong acid. At beginning, since there is no base added, you simply can find the pH of initial, which is negative log of concentration. So negative log of 10 to minus 1 or 0.1, which happens to be 1. So at beginning, you are here. Then while neutralization takes place, there is a very gradual increase or fluctuation in your pH. Once you make it to 50 cm cube, since they are exactly same concentration, the reaction will be neutralized, and there is an immediate jump in the curvature, and it goes straight up, and then about 11 it starts. If you add more base, it's going to break apart, and somewhere in neighborhood of 13, you will never make it to 13, because then again this pOH is 1. When you simply have base and you have overwhelmed your solution and your pH is 13, but don't forget you have dilution. Now what happens at 7, there are a number of ways you can do this. You can take the second derivative and you will find out 7 is really your inflection point when the slope has changed. And this is what we refer to as an equivalence point. So 7 is your equivalence point, and it's when moles of acid is equal exactly to moles of hydroxide. So when there is no base added, your pH is 1. Gradually you add. Once you have 50 cm cube of KOH, you have neutralized, and if you go even half a centimeter cube more, 50.5, you will reach to your destination, which is the maximum pH of that solution. So this is a strong acid, strong base. In this case, I'm adding base to my acid. Let's look at case number 2. Case number 2 is a weak base added to strong acid. So then again, you have a strong acid. In this case, you have your HCl in a flask, few drops of indicator, and then you are going to put a weak base into it. So at beginning, then again, you simply have your acid in the flask. Its pH is at 1 because pH of negative log of 0.1 is 1. So that's your pH. Gradually you increase. Now let's just talk about the salt. The salt is coming from strong acid and a weak base. So it should take character of the strong, so this is acidic salt. So it has a pH of less than 7. And that's why I have 5.5 as sort of a highlighted data. Then again, you come here, gradually there is an increase. Once you make it to 50 cm cube, which is equal moles of both, you will go up sharply, and then you break apart, and then you will end at pH of almost 11 or lesser than 11, because now you simply have a basic solution here, ammonia. So your equivalence point is about 5.5. Nothing so crucial about this case, except remember it once I do my case number 4, I want you to come back to this. What happens if we change the scenario if you add strong acid to the weak base, what's going to happen. Now let's look at another case before we talk about that. Case number 3 is also very important when you have a strong base added to a weak acid. So in this case, I have ethanoic acid. So ethanoic acid, your weak acid is sitting in the flask, and here in your burette, you have your NaOH being added to it. And the reaction goes. At beginning, you simply have a weak acid. By now, you know how to calculate a pH of the weak acid. Weak acid has an equilibrium with water. I just write it to say you can do the calculation plus H3O plus. And here, if you do ice calculation, remember you have 0.1 minus X, you have X, and then you plug it into Ka, and you find your X, and X is your H and pH. I'm not going to bore you with that, but the pH of the solution without any base being added to it is 2.8. Now, in case of a strong base weak acid, you don't go straight smoothly. Rather, there is an immediate jump, and then you come back gently. But let's just talk about salt, then I go back to the graph. Now your salt is coming from a weak acid and a strong base, so it's a basic salt, meaning pH should be above 7, and I have highlighted 9.0 give and take. Then you come here, and once you get really close to 50 cm cube, there is a curvature, not very sharp, and you go up, and then you break apart, and you go getting close to 13. Now, this is very important because what you have created before equivalence point, so this is your equivalence point. Then again, it was at 50 cm cube. Neutralization is not function of strength, it's just stoichiometry. So once you reach equivalence point, your pH is 9.0, and if you do an experiment, it comes to life. Now, what's important and crucial is this domain here from almost initial, when you add your base to it, before making to 50 cm cube, this is where your buffer zone is. So you have a buffer solution rather. If you remember, one way to prepare buffer was to have a large quantity of weak acid and a smaller quantity of strong base. So this is buffer. One other very important point is at equivalence point, you can come back. In this case, it's 50 cm cube. Now, if you divide it by half equivalence on your volume, then you can go back to the curve, and you are going to read pH. And this is where your pH is equal to pKa. Rather very important in terms of answering questions and having some labs that are related to this. Why is the case? Because remember Henderson-Hasselbalch, pH was pKa plus log of salt concentration-wise over acid. And this is the case when you have half as much, when there is 25 cm cube of this. If you do the moles, this becomes limiting reactant, and you will create exactly the same amount of moles of salt as your leftover acid. And this quantity, concentration of salt, is really equal to concentration of acid. You can do the calculations at half equivalence point. And then you remember that if the two are equal, that's log of 1, and log of 1 is simply 0. So pH is equal to pKa. Extremely important, just realize it and remember it for sake of exams. And now let's look at the last case I want to talk about. Is almost case number 2, except I'm reversing it. This time I'm adding a strong acid to a weak base. So what I'm doing is, in my flask, I'm going to have my weak base, which is ammonia. And in my burette, I'm going to have my strong acid, HCl, and I'm going to add it dropwise. Let's see what happens. Since I simply have a weak base, then again, the weak base by itself is going to Remember, it's going to establish an equilibrium with water to give you NH4 plus OH minus, and then you have Kb, and if you go through the whole ice sort of calculation, you have 0.1 take away x, and you have x and x, so you have x squared over 0.1. You find your x, which is OH, you take negative log, you subtract from 14, and you come to answer of neighborhood 11. So this is initial as what you have. Then again, this is a sort of, you have a strong acid and a weak base, so this is a rather acidic salt, and pH should be less than 7. Now what happens is you're going to come, you go through neutralization. Once you make to 50 cm cube, you come down and then you will get close to pH equal 1, because that's pH of your acid by itself, but dilute version of that, and your equivalence point is less than 7. In this case is almost 5.5. I made it up, but it's close. So this is equivalence point. Now what's the difference between this case and case number 2 is, if you do it like this, then you have created a buffer zone here before your equivalence point. This is your new buffer. So if you want to make a buffer, you can have a large quantity of a weak base and a smaller quantity of acid. And if you find your equivalence point, you can come to your x-axis. So let me just do it a little bit nicer. And then you're going to divide that volume by 2. And then you go to your curvature, and you will read your pKb for the base. I wanted it to fall on 9.25, but I didn't draw my graph properly. So this is where your pKb comes to life. So at half equivalence point, concentration of your salt is equal to concentration of the base. And if you remember Henderson-Hasselbalch for bases, POH was equal to pKb plus log of salt over base. And at this point, this is where you have these two terms equal to each other, and it goes away, and pH is equal to pKb. Now, if you don't mind, just compare it to case number 2, and you see what I have changed. The order of adding has been reversed, and something important comes to life. Good luck.